Assalamualaikum and a very good day. Today we from Group 8 we will be presenting about our problem-based learning, Mathematics for Mechanical Engineering, lecture Puan Nur Amirah binti Jumaat. Our group consists 4 members in total, Muhammad Zulfaqar bin Hassan, Nur Alia, Muhammad Rizwan and also Nur Alisha. Growth and decay are mathematical concepts that describe how a quantity changes over time. So these changes can be represented using exponential functions because the rate of change depends on the current value of the quantity. So exponential growth occurs when a quantity increases continuously over time, while exponential decay occurs when a quantity decreases continuously. So examples of growth can be seen in population, increase and also compound interest, while decay can be observed in radioactive substances. So by studying growth and decay models, engineers and scientists can understand better and also predict changes that occur in real life situation. So one of the application of exponential decay is Newton's law of cooling. So this law explains how the temperature of an object changes when it is placed in an environment with a different temperature. So according to Newton's law of cooling, the rate at which an object cools or heats is proportional to the difference between the object's temperature and the surrounding temperature. So this means that an object cools down faster when the temperature difference is large and more slowly as its temperature approaches. So the law is widely used in engineering and science to analyze heat transfer processes and also the temperature changes in various systems. So in conclusion, growth and decay models and Newton's law of cooling are important topics in mathematics because they demonstrate how exponential function can be applied to solve real world problem. So by understanding this concept, it helps students to develop problem solving skills and provide a foundation of studying engineering application involving changing quantities and temperature variation over time.
Assalamualaikum. My name is Nur Alia. My matrix number is AA251798. Today I will present our case study for question A, which consists of part A, growth and decay, and part B, Newton's law of cooling. For part A, the case study focuses on the declining population of white deer in forest ecosystem. In 2010, the deer population was reported at 2,000 due to habitat destruction, deforestation, and human activity. The population decreased to 1,200 in 2020. Since the decline followed an exponential decay pattern, we need to develop a mathematical model to predict future population trends. The objective of this study are to derive the deer population equation, predict the population in the year 2030, and determine when the population will fall below this critical level of 500 deer. Next, we'll move on for part B. The case study involves estimating the time of death using Newton's law of cooling. A dead body was discovered in a hostel room with a room temperature of 70 Fahrenheit. The body temperature was measured at 85 Fahrenheit when discovered and decreased to 80 Fahrenheit 1 hour later. The normal body temperature before that is assumed to be 98.6 Fahrenheit. Using Newton's law of cooling, we will develop a cooling model and estimate the time elapsed between the victim's death and the discovery of the body. These two case studies demonstrate how differential equations can be applied to solve real-life engineering and scientific problems.
My name is Muhammad Rizwan bin Amir and my matrix number is AA251935. Now, I will present manual solution for part A. Since we are from group 8, the question given is number 8. According to the question, it is stated that the initial deer population in 2010 was 2,000 deer. After 10 years, in 2020, the population decreased to 1,200 deer. So we use the exponential decay model, and the equation are y of t is equal to a times with the exponent to the power of kt where A was the initial number, K was decay constant, and T was times. But we change A with P0 according to our questions. For the question A, we need to make a full equation for this question. So we need to find the value of K or decay constant, so we can build a whole formula. To find the decay constant, K, we substitute the known value into the equation. By replacing P of T with 1200, P0 with 2000, and T with 10 years, we obtain 1200 is equal to 2000 times e to the power of 10k. After simplifying and using the logarithm rules on both sides, we find that k is equal to the negative 0.0511. Therefore, our whole equation is P of t is equal to 2000 times e raised to the negative 0.0511t. Next, for part B, we need to predict the deer population in year 2030. Since 2030 is 20 years after 2010, we substitute t equal 20 into the equation. And after the calculation, the predicted deer population is approximately 719.75 deer. Therefore, the deer population in 2030 is approximately 720 deer. Next, for the question C, we need to determine the time when the deer population will drop below 500 deer. We start by setting the population equation less than 500, and our equation is 500 is less than 2000 e raised to the negative 0.0511t. Dividing both sides by 2000 give 0.25 is less than e raised to the negative 0.0511t. Next, we use logarithm rule on the both sides and solving for t, given t is greater than 27.13 years. Since the population model started in 2010, we add 27.13 years to 2010. This gave approximately in 2037. Therefore, the deer population is expected to fall below 500 deer around the year 2037. For the Excel part, the same exponential decay equation was used to calculate the deer population over time. The table on the right shows the population values from year 0 until year 28, while the graph illustrates the decreasing trend of the deer population. From the graph, we can clearly observe that the deer population decreases exponentially over time. When comparing the Excel results with the manual calculations, both methods produce the same values. This confirms that the Excel formula was implemented correctly and accurately represents the exponential decay model. In conclusion, both manual calculations and Excel analysis show that the deer population continues to decrease over time, reaching approximately 720 deer in 2030 and dropping below 500 deer around the year 2037.
Next, we will go to manual solution. Part B, question A. We use Newton's law of cooling to determine the time elapsed between the victim death and discovery of the body. The general equation of Newton's law of cooling is T represented as time equal to TA plus T0 minus TA time E power of negative KT. In this equation, TA represents the ambient temperature or surrounding temperature. According to the question, the room temperature remains constant at 70 degrees Fahrenheit. Therefore, TA is equal to TC, which is 70 degrees Fahrenheit. While T0 represents the normal body temperature at the time of death, which is 98.6 degrees Fahrenheit. Substituting this value into the equation gives us T equal to 70 plus 28.6 times e power of negative KT. When the body was discovered, it is Its temperature was 85 degrees Fahrenheit. By substituting this value into the equation, we obtain e power of KTD equal 15 divided by 28.6. 1 hour later, the body temperature decreased to 80 degrees Fahrenheit. Therefore, we let the time be TD plus 1. Substituting this information into the equation and simplifying, we obtain e power of negative k equal to 2 over 3. Taking the natural logarithm of both sides to this, k equals 0.4055. Next, we will substitute the value of k back into the previous equation to determine TD, which represents the time elapsed between the death and discovery. After solving the equation, we obtain TD equal 1.5916 hour. Converting this value into minute gives approximately 95 minutes. Therefore, the time elapsed between the victim death and the discovery of the body is approximately 1 hour and 35 minutes. In conclusion, based on Newton's law of cooling, the victim had been dead for approximately 1 hour and 35 minutes before the body was discovered.
Hello, I am Nuralisha Umaira binti Azrin Shah, AA250851. I will be doing the reflections now. This problem-based learning project successfully bridged abstract calculus with practical engineering by applying first-order differential equation to the real-world scenarios, modeling an environmental population decline, which is k equals to negative 0.0511, and calculating a forensic time of death with a 1 hour and 35 minutes via Newton's law of cooling. Beyond the math, by using Microsoft Excel, E of T versus T serve as a vital exercise in technical validation, confirming the total accuracy of our manual logic. And by collaborating as Section 5 Group 8 under Puan Numairah binti Jumaat, ultimate strengthens our divisions of labor, communication, and engineering problem-solving skills, all of which are essential for our future career and visually documented in our work presentation.